So as we continue with chapter 2, the next thing that we're going to look is at how to capture an immediate 32-bit constant. And we know that we can get a smaller constant as part of the immediate format, and but sometimes we need more than that, what that field allows. So the ISA provides a couple of instructions to help us with that. One is the move wide with zeros combined with a shift, which are going to allow us to essentially capture the upper half of that 32-bit constant. And then the next one is move with keep, which is going to allow us to get the lower half of that 32-bit constant. So these are specific instructions in the ISA that the architects realized that they were useful. So they are putting this in the ISA, and I want to demonstrate how to use that to capture 32-bit constants. So let's say that we want this 32-bit constant in register register 9, and we know that the registers are 64 bits. So the first thing that we could do is to move an immediate value. So this is actually a byte, which is this byte here, and shifted by 16 bits left and filling with zeros. So that's what the move with zero means. So then we're going to load that value, and it's going to get shifted. So the contents of the register is going to have that upper half here. Then we can capture the second half, the lower half, with a move with keep into the same register without doing a shift. So now we are capturing the lower half, we are not shifting, and the keep refers to keeping that part that we loaded previously. So with those two instructions, it allows us to load a register with a 32-bit constant. So it takes two instructions instead of one when we had a smaller constant. But remember that the idea and the compromise is to make the common case fast, and then still have the ability, perhaps through some compromise, for the user to do what she intends to do. So we know, or the architects know, that loading immediate 32-bit constant is not a common case, but at least the facility is there, although it's not as efficient as the common case, which is the smaller constants. Now let's switch gears and and discuss addressing formats. So addressing formats are different than instruction formats. The definition of an addressing format is it defines where the operand is, how you get to the actual operand that you're going to be, that the instruction is going to be operating on. And there is a relationship between addressing format and instruction formats, because different addressing formats will use the instruction formats, of course, and there may be overlaps. It could be that two different addressing formats may use the same instruction format, or so essentially that's the overlap. So let's look at the addressing formats available in the ISA, in the reduced ISA of the ARM processor that we're going through. The first one is called immediate addressing. So immediate addressing refers to the fact that the operand is built into the instruction. And of course, it uses the immediate instruction format. But those are two different concepts, even though they use the same terminology. So that would be the immediate addressing. The operand is immediate, built into the instruction. Then we have register addressing. That means that the operand is the content of a register in the register file. So that uses the register instruction format, but the same comment applies. Then we have the base or displacement addressing, where the operand, whether it is a byte, a half word, a word, or a double word in memory, you get to the address of that operand by combining the contents of a register with some displacement, some immediate displacement. Okay? And then another format is the PC relative addressing. So this is used in the branches because you are, in this case, your operand is the address in program memory that you're going to branch to. So that uses the contents of the program counter combined with an immediate address, and that's how you get to the address where you're going to jump to or branch to. So those are two different and important concepts to understand, and understand that they're different. Addressing formats or addressing modes versus instruction formats. And this is a summary of the instruction formats. So here we have register format. We have the two registers that are the sources, RM. We can specify a shift amount and the destination register. This is used by arithmetic. This format is used by arithmetic instructions. Then we have the I format, the immediate, also used by arithmetic instructions, where we have a destination register and we have the contents of a register and an immediate field. So in this case, this format is used in two different addressing modes to get to two different operands. The addressing mode for this source register is register addressing mode. This one is immediate addressing mode. Then we have the D format, the data transfer format, which is used by the loads and the stores to get data in and out of memory and into the register file. And that combines the contents of a register and an immediate field, and that operand becomes either the address where we're going to store the contents of this register, or it becomes the contents that we're going to store into this destination register. We have the B format, that's for unconditional branch format, which is just the opcode and the address that you're going to branch to. Then we have the conditional branch format, which has the register that is going to be tested for the condition. So in that case, that is register addressing, and an address that is going to be used in PC relative addressing format. And then we have the wide immediate format, which is very much like immediate, but it only has a single immediate field and a destination register. So that gives you an idea of the contrast of addressing modes and how they fit in the context of instruction formats. The instruction formats is what drives the implementation of the hardware primarily. And of course, the actual opcode, what the instruction does, drives from an implementation in the hardware what the instruction, how the instruction gets to the operands, and what the micro instructions have to do to execute that instruction for that format. So again, hopefully you can see the contrast here. Okay. So let's go through those and give you some examples of some actual instructions. So this is the immediate addressing. So here we have add immediate of this source register with 7. That's the immediate value. And we're going to put the result in register X1. So that's an easy way to essentially load a register with a value is to add it with the register 0. Now let's look at register addressing. So here we have 2 registers, which are the sources, and we put the and the destination register is X1. So in this case, X1 gets the subtraction of X2, or the contents of register X2 minus the contents of register X3. Base displacement addressing. So the operand is in memory, whether it is a byte, half word, or double word is given by the instruction. This is for a word. So here, the address where the data that we're going to load into register 9 is formed by adding the contents of register 10 and this immediate constant. And this is the register transfer notation. So register X9 gets the contents of memory at address given by register X10 plus 32. And then we have PC relative addressing, where the operand address, the actual, what we call the target address of the branch, is the program counter plus the offset from the program counter times 4. Why are we multiplying times 4? Well, because our addresses are in byte, but by definition, the program is in words. You don't have a program instruction that does not fall in boundaries of 4 bytes. So the hardware is doing this. There is no need to put the last 2 zeros, which imply the multiplication times 4, to put that into that immediate field and essentially waste 2 bits of the field, because we know that the address of instructions are always going to be terminated such that the least 2 significant bits are 0, because they are boundaries of 4. Each instruction takes 4 bytes or 32 bits. So an example would be conditional branch on non-zero. We're going to test the contents of register 11, and we're going to branch to exit. Now, the compiler or assembler or the linker, depending on how the tool chain behaves, is going to compute and resolve the actual value that this label needs to have, relatively speaking, from the program counter, the value of the program counter at this instruction, and that's what's going to be put into the field of the instruction itself. Okay? So we're going to resolve this address as the program counter plus the offset, which is this one, times 4. So at this point, we have seen a lot of all the different instructions. So it's appropriate to give you a sneak peek of what we're going to be covering in chapter 4. That is the longest chapter of the course, where we're going to actually be implementing this instruction set, or actually a subset. We're going to be implementing a subset of the subset, just a handful, but it'll give you a good idea. And we're going to be implementing the processor in a couple of ways, but this is the simplest one. This would be what is called a single cycle data path, where all the instructions are executed within a single cycle of the clock. Now that may sound pretty good, but it's actually not, because then for everything to happen within a single clock, what happens is that you have to slow your clock down a lot, so you cannot have a fast clock. And we'll see, we'll look at techniques, implementation techniques for the hardware that we'll do to make sure that the clock can run much higher. But this is the simplest implementation. So you can see here that how the hardware is starting to take into account and be subordinated to that instruction set that we specify. So that instruction set becomes a specification, and the hardware is just implementing it, not the other way around. So a specification is the bulk of the work. Once you have that well specified and well articulated, then the implementation is pretty straightforward. So here you can see 2 memories, and remember, the memory really is not part of the processor. They're going to be outside of the processor. In this case, in modern processors, these 2 memories represent the level 1 caches, which are split in a Harvard memory organization, which means that you have 2 separate buses for data and instruction. So you have an instruction cache and you have a data cache. So that's what this abstracts. But you can see here that the instruction is coming and the fields are getting a split. These are the fields of the instruction formats, so that the hardware can do something with it, and that means something. So for example, the opcode, which are the upper bits of the instruction, is going into the control unit. And in this case, the control unit is combinational, because we're doing everything in a single cycle, and we're deriving from that the actual control signals, which are in blue. So this becomes essentially a combinational logic block. And you can derive the truth table for that and implement it. So here, the fields for the register file, this is the register file, for the register file are being extracted. And remember that sometimes for the second source register, sometimes it comes from this field, sometimes it comes from this field. So how do we know that? Or how does the control know that? Well, it knows it from the instruction opcode, and then it can generate control into that mux to steer the appropriate register that we want to read as a second register. And then the contents of the registers show up here. And they go into the ALU. And sometimes the second input of the ALU sometimes comes from a second register, but sometimes it comes from an immediate field. An immediate field that has to be extended because the ALU, as we said, the data path is 64 bits. So it has to be sign extended. That's pretty easy. That's just copying the most significant bit. But this is the immediate field that sometimes we use. Again, the controller from the opcode knows whether we have an instruction that requires the data from a second register or from an immediate field, and it steers the data through that mux appropriately. It also knows what the ALU needs to do. So we have some secondary ALU control here that uses the field of the instruction, which is the, it could be the shift mount or some other function code for the arithmetic instructions, and combines that and tells the ALU what it needs to do. Here we have a 0 flag, so we know when we have equality to branch. What else do we have here? Sometimes this represents an immediate operand which goes through this mux here to the ALU, but sometimes that immediate is a branch target. So here we are doing the multiplication times 4 and going into this adder that is going to add the program counter with the immediate field multiplied times 4, and it goes into the mux here. And the controller knows that if we have a branch and we have a 0 out of the ALU, then we're going to take the branch. So it's going to force the next value of the program counter from this input of the mux. If we don't take the branch, then we're just going to execute the next instruction. And that takes this path here. We get the program counter, add 4, because that's the next instruction, is 4 bytes above, and we're going to go through this input, and that's going to be the next instruction that we fetch from the instruction memory. And the whole cycle repeats again. What's going on here? Well, sometimes the result of the ALU, like on an addition, that needs to go back into a register. So it goes through here to the right data, and we have a right register address here. Again, the controller knows how to steer the data through muxes. But sometimes what comes out of the ALU is the content of the register plus some immediate value, because we are doing a load or a store, so we get an address. What we get is an address, and we read that data, and it comes back to the register file, so that would be a load, or sometimes that address is a store. So it's coming from the register to be stored through the right data port of the memory. And again, the controller knows whether to force the memory, the data memory, to write, to take this data, or just to be read. So hopefully this gives you a quick idea of how you can put hardware together, hardware that you're familiar with at some level of abstraction. This is not a schematic. This is an implementation diagram of the architecture, but hopefully that gives you some idea. And you're going to get to practice with this, because in the lab, you're going to implement this in Verilog and simulate it. So let's look at just some more examples of targeting addressing. Let's look at this statement of C code, which I think we looked at this already. So I'm going to pass. Yeah, we looked at this already. We're going to go through this quickly. We use some animation here. All right, so let's talk about another very relevant topic, which is synchronization between two processors. So you know that modern processors these days are multi-core. So let's just take the simplest case of a multi-core implementation, which is two cores, two processors that are going to be sharing an area of memory. So how does that happen from an organization perspective? So usually what you would have is that each processor, the level 1 cache, just like the figure that we looked at, is going to be private to each processor. So each processor is going to have its own set of level 1 data and instruction caches. But as we'll see in chapter 5, the cache organization and architecture is sophisticated. It's multi-level. These days, is the usual is to have 3 levels of cache. But by the second one, for reasons that we'll go and explain at length in chapter 5, and why you want the caches that are closer to the processor to be smaller for a speed sake, because you want to run at the fastest speed that you can. But then as you get removed from that top of that memory hierarchy, you have larger caches, but they'll be slower. And we'll talk about how to simulate and determine what are the best parameters to choose if you are designing a memory hierarchy. So in today's processors, we have 2 processors. Each one of them is going to have its own data and code cache. But then at a lower level in that memory hierarchy, you have level 2 cache, which is larger. So now you don't want to have 2 large blocks of memory private to each of the processors. It's not as efficient as just having the private smaller ones. But it is a good idea to have this large cache of memory that serves the overall system. So at that point, the level 2 cache will be shared by the 2 processors, even though they have their own private level 1. And of course, they share everything else below that hierarchy. Once they share something, then they'll share everything else. They'll share the DRAM, they'll share the virtual memory, They'll share the level 3 cache if there is one. So the question is, when you have two processes that are sharing some area of memory, how do you guarantee the coherency of the data? In other words, if processor 1 is going to get some data from that shared area and modify it, and then processor 2 goes and gets that same data, that data is stale. Now that data is old. How do you keep coherency and the correctness of the execution stream, which is what the programmer intended? So that lack of coherency is what we call a data race. And what the way to solve it is to have synchronization of the execution between the processors. And this requires some hardware support and also some ISA support in the types of instructions that are part of the instruction set. So one way to do that is to offer what we call atomic read-write memory operations. And that terminology, atomic, means that it's indivisible. There is nothing that can happen in the system while that instruction is being executed. So that guarantees, by design, by hardware implementation, that there is not going to be a data race. So this type of instructions usually are the swap of a register with memory data, or you could have atomic pair of instructions. Again, the idea is just to guarantee that one processor is not accessing memory or is not accessing data that is being modified by another processor without its knowledge and not being able to do anything about it, which will result in faulty program execution. And there are other techniques as well where the processors can snoop on what the other processor is doing. But this is your first course in computer architecture. I think that the idea here is for you to be aware of these issues and techniques. So what type of instructions do we have in this ISA that we are studying? So we have a load exclusive register and a store exclusive register, and those are the mnemonics. So to use these instructions, what we do is that we execute the load and the store with the same address. And if there is a change to the address, that instruction is going to fail and is going to be communicated via some output register, which is really a status register. And then, and that's why it's important that these things are part of the ISA, because they become policies and rules that the compiler needs to be aware of to be able to compile code that runs correctly on the processor. I'm referring to the last bullet. Only use register instructions in between. So the compiler knows that only register instructions can be used between these two instructions. No access to memory in between them. So that aids with the data race issue. So here's an example of an atomic swap. And here we are loading a register and storing, and then register 9 is the status register. and we test register 9. If it's non-zero, we keep trying. Only after we have been successful, then we can move the contents of what we loaded safely into another register. So this is a sequence to test and lock a variable that is being associated with another register. So here's an example of copying a value. So basically we're setting register X11 to 1, and then we're going to read a lock. If it's 0, we just keep waiting for the other processor to release the lock. Once the other processor releases the lock and this register becomes 0, as I mean, the lock is in memory. This is the actually the memory address where the lock is. The lock variable is stored. That address is in register 20, and we're putting it in register 10. Once that register is 0, then we can use that memory location, and we try to store. If it fails, we go through the sequence again. And when we are successful, we know that the other processor is done with that location. We free the lock. So that gives you some ideas. Again, we're wrapping up the chapter and we're just introducing different concepts just for you to be aware of it. I cannot really say that is the main idea of the chapter. I think that once we went through all the instruction formats and the addressing modes and all the main instructions in the ISA, as we wrap up the chapter, we're just sort of compiling different topics for completeness that you should be aware of. So here's another one. The idea of how programs end up in memory to be executed. So let's say you have a C program, and you're going to compile it, which could give you assembly language, an intermediate assembly language program, and then the assembler converts it into object code, which is the machine language of the ones and zeros, the binary. This operation, I've talked about this operation, how you can parse the lexicon of the specific language and convert using those predetermined blocks that we looked at for the different structures into assembly language. And then the assembly process is very simple. This is a lookup table. You just look at the instruction and what those instructions are in bits, and you convert it to binary. And that's why many compilers do this in a single shot, and they also do optimization. So once you have the object code for that specific program may be using library calls. Any type of sophisticated program is going, or even not that sophisticated, is going to use libraries. So there is another function here, the linker, that links the actual code of your program with the objects that you have invoked in your program. That's part of the linker. And those two combined become the executable program. And then that's what gets loaded in memory and executed. by a loader. This is a function of the operating system to essentially read that binary from the disk, put it in memory, and then go and execute at that location where it was loaded. Normally, on something like a PC, this code will be what is called relocatable code, meaning that it is the place in memory where it resides during runtime is not hard-coded in the binary. It can be loaded in different places of memory. And with the aid of registers, then the program will run correctly because everything will be relative to some memory location that the loader put the code at, and that the loader is informing the program what that is. So through relative addressing, and that's why it's so important, then this code will run correctly, even though it may not be loaded in the same place of memory every time that it gets run. So furthermore, this type of linking is what is called static linking, because you're bringing the objects of the library that you are invoking right into the executable that you're going to store and run. So this slide is just basically the what I said. So I'm going to just go through that. And you'll get the slides, and it's always good that you go over them again and read them in detail. So the other way of doing linking is what is called dynamic linking. And modern operating systems, such as Windows, they use dynamic linking almost exclusively. And you're familiar with DLLs, dynamic link libraries, that come as packages that are part of the operating system release, or if you are doing some development of software that is more specific and doesn't come with the operating system, you may get those DLLs from whoever is providing you the libraries. So the idea behind dynamic linking is that it makes overall code size more efficient, because that dynamic link library could be used by many different programs. So imagine the graphics that make up a Windows program that is used by any program that runs in Windows. So the Microsoft Foundation libraries, the ActiveX, all those type of dynamic link libraries, they are used by almost all programs. So it would be very inefficient to have the same binary built in every program. The programs would be huge, and essentially it'd be a huge waste of space and very inefficient. So the idea is that since these libraries are used by many programs, make them part of the operating system and link them dynamically during runtime. Okay? So essentially that requires that the code be relocatable, which all codes are, if they're running on a sophisticated operating system like Windows. And the other benefit is this one, that let's say that the library got updated. Well, you don't have to recompile and relink your code, because the library gets updated independently of your application. So when that library gets updated or a bug gets fixed, you don't have to do anything to your code. As long as the API, the application programming interface, remains the same, which is of course the best practice, your program will continue to run and bring in the newest library. So that's another very desirable feature of dynamic linking. All right, so more different topics. We have seen this already, so I'm going to go through this quickly. These are things that you should still, I mean, they are in the slides, so you study them when you get the slides. Now let's talk about the effects of compiler optimization. So I've explained the rudiments of compilation, but compilers do much more than that. They actually do optimization. That's really where they excel at. And now that you also know about benchmarking and how to gather in data of performance, these are some graphs which you could look at to compare different levels of optimization and their impact on compile code and on code execution performance. So you could look at these types of graphs. So compilers could have different levels of optimization, from 0 to, in this case, we're looking at 3 levels of optimization. Why 3? Well, it gets more sophisticated as you go up in levels. Most of the lower levels are mechanical in nature, in which there are well-known algorithms, but they start after that transition to be more heuristics based and very dependent on the provider of the compiler. So what happens is that you can usually get compilers with no optimization for free, because that's pretty easy to do, but to get the higher levels of optimization, you have to pay a license fee or a premium. So here we have compile code with different levels of optimization for Pentium 4 on the Linux. And here we're looking at the performance. Remember, the performance is defined as the execution time, okay, or 1 over the execution time. But here we have normalized the execution or the performance without optimization to 1. And now we're looking at the different levels of optimization. So here it could be said that the higher levels of optimization don't buy you much more for this specific program. But just having 1 level of optimization, you can more than double the performance of this program. What happens to the instruction count? Well, here we have about 110, 115,000 instructions. And with the different levels of optimization, we see that the first level does the best, where we have about 1/3 of the instructions. So it shaves the program size, the static program size, by about 66%. This is another way of looking at performance. How many clock cycles does it take for the program to execute? So again, we can see that this is about 160,000 clock cycles, and with optimization, it runs much faster. These two graphs are related, performance and clock cycle. They're not the same, but they're related. Also, something like this is interesting. When you're looking at the clocks per instruction, and we see that without optimization, the clocks per instruction is lower on average than with the other optimizations. And here we have that the first level of optimization is actually choosing, we can infer from this graph that it's choosing more complex instructions because we have a higher average clock per instruction in the program. While this, as we go up in optimization, the highest optimization level is using sort of mostly the same type of simpler instructions of the non-optimized case, but we're also getting a lot of performance improvement. And here we have a little bit more of code size because the instructions are not as complex as in the optimization one, and this is why this is the lowest, but the performance is about the same. So when you look at it, you can infer that yes, level 3 of optimization does a superior job when it comes to giving you a smaller program that has a high performance. So this is the type of data that that we discuss in chapter 1, how to look at this data performance for the specific programs to make architectural decisions. Because when you are choosing, for example, what is the mix of the introduction of a specific instruction that may change the dynamics of the CPI for a specific compiled program, you would run a model of your architecture and you will run it on an actual program and look at this data to make decisions. Is it worth putting these other instructions with perhaps lower CPI or with perhaps some functionality, some specific functionality? Does it, how much do we get in performance improvement because of that? So this is the type of data that you may look at during the architecture of an instruction set, although here we're just comparing different optimization levels of a compiler. The algorithm also has bearing in the efficiency and the performance of a specific program on a specific processor. So here we're looking at three implementation algorithms of the sorting procedure. So we have bubble sort, quick sort, and quick sort. This is actually, I'm sorry, this is the comparison of quick sort versus bubble sort. But here we have bubble sort with no optimization, with a different optimization, with Java, and Java with the just-in-time compiler. This is the performance. So higher is better. And here we have the same for quicksort. And if we compare the two here in this graph, this is the speed up. We know that quicksort is better of quicksort with respect to bubble sort. Remember that this is normalized for each program. So this doesn't tell you anything about absolute numbers. It's just comparing all these different 6 cases. And it's relative because it's normalized to the C non-optimized case. Same here. So there are no absolute values here. It's just the relative, the relative of these 6 cases with respect to each other, but normalized to the C non-optimized case. But when you compare both with the actual execution times and performance, Quicksort has a 2,500 times a speed up. So that means that it's 2,500 times faster Quicksort, that algorithm, than bubble sort with non-optimized code. And it's overall is better, and we know that. But this shows it for the different optimization levels for Java and for Java with the just-in-time compiler. So it's important to be able to put data like this together, because that gives you insight how an architecture responds to real programs. Another issue is array indexing versus using pointers. Not all languages support pointers, but you know that pointers correspond to direct memory addresses. So that can avoid indexing complexity and calculations, so it tends to be more efficient. For example, clearing an array using pointers versus using an array. So here's the array implementation, okay? And I'm not going to really go through the specifics, but this would be the implementation by using pointers. Another strength of using pointers with array manipulation is that the multiply can reduce to shifts, and that's very useful. A shift operation is much faster than an actual multiplication. And many optimizations that the compilers do is to change your expression of array indexing to using pointers. That's an optimization. And you could do it yourself, but if you have a good optimizing compiler, that's one of the optimizations that could be done. So we are wrapping up. And again, we're very close, but I don't know if we can do it. So you know, the ARM is the most popular embedded course, so we talked about that. We used to teach with MIPS, which is very elegant, but it's not used. It is used in the embedded market, but not as widely used as ARM. But it is a very elegant instruction set, MIPS. But this is just some comparison of the two macro ISAs, and they date to about the same time, where there was a shift from the complex instruction sets, like what Intel had done, to RISC, so reduced instruction set architecture, which idea was to have simplicity in hardware to achieve high speed and let the compiler make use of that. So that's just some statistics of the both ISAs. They're very similar, although the ARM is a little bit more complex. These are the instruction encoding for. This is what we are studying, leg V8, this is MIPS, and this is the ARM V7. So just some, you can see how things change. It's not an exact science. It's actually architected by people, and they're going to have their biases and their experiences, and they're going to bring that with them. But so you can see the difference there. Now we wouldn't be able to finish this chapter without talking a little bit about the Intel x86 ISA, which is also pervasive. So here's some of the history of it. Again, I'm not going to read it to you. I do want to finish the chapter, but you're going to get the slides, and you're going to be able to there have been books written about the evolution of the Intel architecture, but you're going to be able to read about that evolution in these slides. The one idea that we do want to mention is that it is an architecture with complex instructions and very few registers. You can see here, this is the register file of the Pentium compared to, let's say, 32 64-bit registers for ARM. But the instructions, what the instructions can do can be very complex, and they use these registers in different ways. So they take a lot of cycles. Although the Intel is like two processors in one, there is an actual RISC engine that serves a number of RISC-like instructions in the ISA of the Pentium that compilers favor. And the reason the older complex type of instructions are there is because it's important for Intel that the processor has backward compatibility, and that any code that was ever compiled runs on that Pentium without compilation. That's an important part of their philosophy. But that's made the ISA very bloated. We'll see that later on. So these are the memory addressing modes of the Pentium, 2 operands per instruction. So we have register, we have base register with displacement. So we have that too in the ARM. We have base register with the scale of another register. And we can also have register with a scale of another register plus a displacement. So that gives you just a contrast of the different things that could be done just from another ISA perspective. And here are the instruction formats. One starting, one glaring difference is that Intel has a variable length of instructions. That actually makes the hardware more complex for fetching, because it needs to know what type of instruction before knowing whether it needs to go and get more as part of that instruction. In ARM, they are all 32 bits. We know that we have to get 32 bits, period. Here, we have instructions that are a byte, or we have instructions that are 48 bits. Okay? So, let's keep to this. Mostly what I've been saying is in these slides here, in this section. But this is a graph of the number of instructions through time. And as it's a bit dated, this graph, but as 2012, we were about 900 instructions in the ISA. I'm talking about the actual assembly language instructions. And that's because as they evolve the processor, they're still carrying the older instructions, again, for backward compatibility's sake. Okay, so I think we'll be able to wrap up the chapter today, and I'll be assigning homework. So we'll start chapter 3 next time. You get the slides, you can read this last few. So to summarize, remember these design principles. Simplicity favors regularity, so we want regular design. So it's simpler, so it's smaller, so it's faster. And we want that design to serve the common case because it's like getting the most bang for your buck, or essentially investing what it matters when it comes to design efficiency. But without losing sight that good design demands good compromise. So that you cannot be favoring simplicity so much that you really have a bad design because it's too limited. So we talked about layers of software and hardware. So hopefully you have a clear idea how hardware and the compiler assembler interact. And we looked at the leg V8. You saw contrast with the x86. Some last additional features of the ARM V8, which again the leg is a subset of it. Conditional instructions, and we did mention that as we were going through it. Okay. It also has vector instructions. We're going to talk about vector instructions in the context of chapter 3 of arithmetic, same as floating point and things like that. So chapter 3 is going to cover a lot of these two types of instruction. It still has a large number of instructions. Okay. All right, so that's the name of that's the end of the chapter. I'll see very quickly if there are any questions, and we'll adjourn just in time.